we calculate the first, second, and third derivative of the function y equals x to the fifth minus 3x squared plus 2x squared, 3x cubed minus 2x squared minus 1. Very straightforward if we know the rule for a power function. Derivative of x to the fifth is 5x to the fourth. Derivative of x to the third is 3x squared. Multiply that by the negative 3, we get negative 9x squared. The derivative of x squared is 2x. Multiply that by 2, we get 4x. And the derivative of any constant is 0. And then the second derivative is the derivative of the first derivative. So we simply take the derivative of the y prime function. And derivative of x to the fourth being 5x cubed multiplying, being 4x cubed, I'm sorry, derivative of x to the fourth being 4x cubed multiplying by 5, we get 20x cubed. Derivative of x squared being 2x times minus 9, we get negative 18x. Derivative of x being 1, 4 times the derivative of x is just 4. And then the third derivative is equally straightforward. I won't read that one off to you. Okay, the second function is y equals x to the 5 halves. Now, one thing you notice for a polynomial of this nature, you can see that if we continue taking derivatives, subsequent derivatives, well, in the next derivative, that 18 being constant is going to have derivative 0. We're just going to be left with, what, 120x. The next derivative is going to be just 120. And the next derivative will be 0. A fifth degree polynomial, if we take the first derivative, we're down to fourth degree, second derivative down to third degree, third derivative down to second degree. Then the fourth derivative will be of first degree, and the fifth derivative will be of degree 0. In other words, it's going to be 0. Okay. Actually, well, no, fifth derivative is going to be constant. It's going to be 120. And then the sixth derivative would be 0. So the point being that the derivatives of a polynomial function eventually zero out. Okay. That's not the case for a function like y equals x to the 5 halves, and we'll see in a minute why as we go through this. First, y prime, well, this is just a power function. It's going to be 5 halves x to the 5 halves minus 1, and x to the n minus 1. 5 halves times x to the 5 halves minus 1. 5 halves minus 1 is 3 halves. So we have 5 halves x to the 3 halves. Second derivative, well, we got the 5 halves, and then we take the derivative of the x to the 3 halves, which is going to be 3 halves x to the 1 half. 3 halves x to the 3 halves minus 1. 3 halves minus 1 being 1 half. And we can, of course, combine the two fractions. We get 15/4 x to the 1 half. Now, taking the third derivative, I'm going to go back to this form rather than this form, simply so we can see how these coefficients build. So we have what? In other words, there's a pattern to how these coefficients occur when we take subsequent derivatives of this function. Okay. So the derivative of x to the 1 half is 1 half x to the negative 1 half. 1 half x to the 1 half minus 1. 1 half minus 1 being negative 1 half. And of course, I'm not going through the details of applying the power rule. I assume that you know that at this point. If you don't, you should go back and make sure that you're practiced with the power rule, really understand it. And then these derivatives become very straightforward. Okay, so, and of course we can multiply everything out, and we can also express the x to the negative 1 half as 1 over the square root of x. So we have 5 times 3, 15, 2 times 2 times 2, 8, 15 over 8 square root of x. Now there's a pattern to these coefficients. You might ask yourself, what would the next coefficient be? Well, the next coefficient here would be taking a derivative of x to the negative 1 half. So we would get a negative 1 half in this series. So we got 5 halves, 3 halves, 1 half, negative 1 half. And the derivative of x to the negative 1 half is a multiple of x to the negative 3/2, so the next derivative is going to give us a negative 3/2, and it would be profitable, kind of reinforce the whole pattern of the derivatives of power functions. If you were to carry this out a couple of extra steps and see how you think this pattern would continue, see if you can predict what would happen, at least what these coefficients would be, if you went to the 10th derivative or the 20th. There's a clear pattern that you could build. Okay, well, y equals x to the negative 2/3. What do we get here? Derivative of x to the negative 2/3 is negative 2/3 x to the negative 2/3 minus 1, which is going to be negative 5/3. The derivative of that we'll have the negative 2/3, and then the derivative of x to the negative 5/3 is negative 5/3 x to the negative 8/3. Then the next derivative, we're going to have the derivative of x to the negative 8/3, which is going to give us negative 8/3 x to the negative 11/3. Now we can multiply all that out. We're going to get negative 80 over 27x cubed times the cube root of x squared. In other words, x to the negative 11/3 is 1 over x to the 11/3, and x to the 11/3 is x to the 3rd, which is x to the 9/3, times x to the 2/3. X to the 2/3 is the cube root of x squared. And I'm not going to go through the details of that. I will mention that people do not do well with rational exponents and radicals, partly because it's fractions, and fractions are undertaught and underutilized. You know, this is from a previous chapter. You really do need to know how to do this, so you might definitely want to go back and review what we did in class, videos, text, whatever it takes, so that you understand how we get from here to here. If you understand that much, you're doing pretty much okay. Also note there's a definite sequence of these coefficients. The next coefficient would be negative 11/3, and then the next would be negative 14/3, and so forth. Notice also that we have a negative here. We have a negative times a negative, so this one would be positive. We have negative times negative times negative, so this one would be negative, as it is. And the next one would be positive. We're going to alternate positive, negative, because these coefficients, or these exponents, are going to continue to decrease. So once they're negative, they're going to stay negative. With every derivative, we're going to get another negative. Okay. Now, I'm going to do this one on a separate video. I did this one mostly to illustrate another illustration of the chain rule, and an illustration of the fact that this whole thing of taking derivatives can get out of hand pretty easily, and they can get pretty complicated. Even though there's always a rule, you can always do it if you can do it without making a mistake. They get very long and become very error prone. These three are not bad. This one gets kind of nasty. I only go to the second derivative. So you might think about this before you see the next video. How do we take the derivative of this function? How do we take successive derivatives, first and second derivatives? And time and space didn't permit us to go on to the third, but I wouldn't have done it anyway because it just becomes more and more complicated. This is sufficient to show the whole idea of what you do and how complicated things can get.